To extract gold from raw ore like this, the global hydrometallurgy industry has long relied on a single chemical tool, sodium cyanide. This benchmark equation details converting solid gold into a soluble complex, washing it directly out of the ore. Held by weak ionic bonds, sodium cyanide readily breaks apart in water, flooding the solution with highly mobile, free cyanide ions. These free ions make sodium cyanide extremely hazardous. Just 1 to 2 milligrams per kilogram of body weight is fatal to a human. The central engineering challenge is to retain the chemical affinity required to bind with gold, while preventing the lethal biological interactions of free cyanide. This requires a molecule that functions like cyanide inside a rock, but remains chemically inert inside the human bloodstream. In the human bloodstream, cyanide actively targets the cytochrome A3 enzyme, effectively shutting down all cellular respiration in its path. This is the active component of the JIN CHAN agent, a modern metallurgical alternative known technically as carbonized trimeric cyanate sodium. JIN CHAN achieves low toxicity by using covalent bonds and steric hindrance to lock cyanide-like groups within its specific structural geometry. We have to determine if this physical geometry can substitute for the high-mobility ionic bonds that traditionally drive gold leaching. Understanding the solution requires a look at the specific electron-level failure mode of a cell exposed to sodium cyanide. Healthy cells produce energy in the form of ATP through the biological electron transport chain. At the center of the cytochrome A3 enzyme, a single iron ion acts as the primary catalyst. This iron continuously toggles between two oxidation states, accepting and then passing on electrons to maintain the chain. This cycle transfers electrons to raw-unstable oxygen, which activates the oxygen into an O2- state. The activated oxygen then binds with hydrogen ions to form water, releasing the ATP energy that powers the cell. Cellular survival depends on the rapid, unimpeded oscillation of this specific iron ion. Upon entering the body, sodium cyanide dissociates into Na+ and free Cn- ions. The carbon atom in a free cyanide ion carries a lone pair of electrons sitting in an active orbit. This lone pair makes the ion an aggressive coordination agent, driven to bond with empty metallic orbitals. The lone pair locks directly into an empty orbital on the cytochrome A3 enzyme's iron ion. This bond creates a stable complex called cyanide cytochrome oxidase, which permanently freezes the iron in the Fe3+ state. As the iron cycle stops, electron transfer and ATP production fail. The entire transport chain goes dark. The human bloodstream remains fully saturated with oxygen, but the tissue cells have lost the ability to utilize it. This is intracellular asphyxiation, a structural lockout of the cellular energy grid. To bypass this lockout, the JIN CHAN agent uses a different chemical delivery mechanism, as seen in this comparison with sodium cyanide. Sodium cyanide relies on weak ionic bonds, but the JIN CHAN molecule uses rigid internal connections. It utilizes pseudo-cyano groups to provide the chemistry needed to extract gold. These groups are secured to the main carbonized structure by strong covalent bonds, rather than the weak pairings found in cyanide salts. The molecule's large physical footprint also creates steric hindrance, a spatial barrier that blocks unintended interactions. These covalent anchors and the molecule's spatial bulk prevent it from decomposing into free cyanide ions during processing. This structural stability prevents the lone pair attack that typically paralyzes biological ire. This stability allows mining operations to dissolve gold into solution without releasing toxic free cyanide into the environment. The leaching equation shows a larger coordination complex forming between the gold and the JIN CHAN agent. Fitting these bulky molecules around a single, dense gold atom requires a specific geometric orientation. The pseudo-cyano groups maintain just enough flexibility on the molecule's outer edges to bypass their own steric hindrance and lock onto the gold. While manufacturing results in trace residual cyanide, the lack of free dissociation brings the operational toxicity near zero. Iron oxide stabilizers, comprising up to 3% of the agent, further anchor the molecule and prevent decomposition. This macrostructure is engineered with dual precision, flexible enough to envelop gold, but rigid enough to keep its toxic components locked. This comparison illustrates the two target environments, the biological enzyme and the metallurgical gold lattice. Sodium cyanide fails the biological test because its unconstrained mobile ions can fit into nearly any metallic orbital. The JIN CHAN molecule is blocked from the human enzyme by its own steric bulk, yet securely latches onto the exposed gold atoms in the ore lattice. Hydrometallurgical engineering now focuses on mastering spatial geometry to control chemical reactions at the molecular level. This shift represents a move from volatile ionic chemistry towards stable covalent macromolecular engineering. This effectively removes the threat of catastrophic poisoning from massive processing facilities, making industrial gold production inherently safer. Industrial mining is evolving towards these engineered molecules, replacing lethal chemical inputs with structural precision.